Hey guys, welcome to topic 7.1. We're going to be looking at identifying types of chemical bonds. And so, from this lesson, you should be able to identify a compound as having one type or the other, and then just some general characteristics of them. All you need is a periodic table and then the note page. I also want to start by saying I am making this video from home, which I normally don't do. And the rabbits, this is my third time trying to make this video, and the rabbits are not cooperating with me, so please bear with me if Shaylee strikes up another attack on my door. She's been digging at the door like a dog all night, and I don't know what her deal is. So, anyways, on to the actual important stuff. So, just to kind of summarize where we left off from our last unit, the one thing, like I said, is chemistry is the snowball effect, unlike some of your other classes. And this is the first time you're really going to see that where one piece of information is important in the next unit. And so these things are not going to be going anywhere. And so as just a quick reminder, when we write a chemical formula, here's a good example with water, is it tells us two pieces of information. The elements that are in the compound, so water is going to contain oxygen and hydrogen, and we also can establish that it's two hydrogen to one oxygen in a ratio, which is also important as well. So, like I said, the name of the game with this unit is all on bonding. And so, like I said, there's a lot of overlap from our periodic table unit to our chemical naming unit into this one. So, they're kind of interchangeable in that one helps the other. What is just the general definition of a bond? It's a strong attractive force between atoms or ions in a molecular compound. And so that attractive force is all dealing with those valence electrons. And so we have two ways that we can form a bond. We're going to get into that here momentarily. But the two primary ways that a chemical bond forms is through a transfer of electrons while one atom loses, the other gains. And then the other option is sharing. And we've talked about transfer more than we've talked about sharing. This unit, we're going to get into a lot of the sharing side of things with a chemical bond. So, stability is the whole driving force in which a chemical bond is going to form. If you remember back in the periodic table unit, we spent time on the octet rule and then what is easier for an atom to gain or lose electrons to get to that point of having 8 valence electrons. We discovered it's easier for nonmetals to gain electrons and it's easier for metals to lose them. The idea is it wants to get that outermost energy level all the way uh, filled with the two s electrons and two p electrons, and that again makes them like the noble gases. And so, again, stability here does not mean the nuclear stability, but stability in its configuration and those electron arrangements. So here's what that transfer looks like. And you may want to pause it and get something that's two different colors to kind of show where things are going. You'll see here they're using black and red. So red is representing sodium and its one valence electron, and the black is chlorine and its 7 electrons. And so we know that sodium has that one valence electron. It's an alkali metal. It's easier for to lose that one electron and move to the inner energy ring or electron energy level where it's already completed. So chlorine, it has 7. It's easier for it to take in one electron than trying to lose those 7 to then again complete its configuration to become like a noble gas. So you'll see on the right hand side of the arrow is kind of like once we've done this transfer, this is the result. So sodium no longer has an electron, valence electron. It's got those inner electrons to fill, and it's positively charged. Chlorine, notice it's got those 7 black electrons and that one red one representing we now are filled, and it's taken on a negative charge. So that's once the transfer's taken place, that's where the actual chemical bond forms, is you have that positive and negative electrostatic attraction, and we get the compound sodium chloride. So sharing electrons, here's an example. And like I said, we're going to spend a whole lot more time on this. But the premise is it's just like the transfer in that we want to get to 8 valence electrons. This is a unique characteristic that nonmetals tend to do, where a chlorine atom, for example, can come in contact with another chlorine atom, both of which have 7 electrons. And notice that they have one electron that's single and it needs to have one more to pair up with. So what they can do is overlap that part of their configuration. And so each atom is happy now. It has like an octet by sharing that one electron. And so that's another way a chemical bond can form. Again, this is In the nonmetals, we don't see this with metals. So we're going to get into the types of chemical bonds. So an ionic bond is where we have an attraction between two charged ions, and the key word is oppositely charged. So a lot of blast from a past vocab that we've been using for quite a while now. We understand that ions just means that it's an atom that's charged because an atom's not always neutral. Remember, we have two types of ions. The cation is the one that takes on that positive role. Again, it becomes positively charged because you have now more protons in the nucleus than electrons. From that loss of electrons, and those elements that make cations are the metals. So, all those positive charges and the transition metals we use from our periodic table with naming. Anions, on the other hand, is on the right hand side. Those are taken on the role by the nonmetals. They take on a negative charge because they take in electrons, therefore, they have more electrons than they do protons. And so, again, that's from that gain. And so, what happens again in this situation is there is a transfer. So, the metal takes and gives up electrons, non-metal takes them in. And so, when that transfer takes place, we then get a positive charge, negative charge. That electrostatic attraction, that whole idea that opposites attract, is where that chemical bond then forms. One other thing that's unique is they tend to form these 3D crystal lattice structures. And so, this diagram, the green is the sodium and the gray color is the chlorine. Oops, I'm using a touch screen and I'm not used to it. There we go. So, anyways, if you go ahead and take some table salt and sprinkle it onto your hands, even if you don't have a magnifying glass at home, if you look at it very closely, you will see that it's actually cubic in shape. And the reason why it's these little cubes is how it arranges itself at the molecular level or at the atomic level. And so different ionic compounds make different structures. If you guys have Epsom salt at home, Epsom salt is magnesium sulfate, which is another ionic compound. It has a different crystalline structure. And so, because of the atoms and their arrangement, that decides the overall structure that we can see at the macroscopic level because of what's happening at the microscopic level. So, a covalent bond is what we're really going to spend a whole lot of time with in this unit more than ionic. This is with neutral atoms. So, there is no gain, there is no loss of electrons, there's no ions involved. What happens here is there should be sharing of electrons between two nonmetals. And I think my PowerPoint is probably needing a whole lot of updating. The little video is no longer even working. And so, covalent compounds represent or form molecules. And so, this is where vocabulary gets used interchangeably when it's not always correct. Ionic compounds do not make molecules. Covalent bonds can make molecules. So a molecule, if you take a look, the three below are all examples of molecules. So NH3 in the middle is ammonia and H2O is water. Those are compounds. We can see two different elements and they have a fixed ratio. However, the one on the right is chlorine. And you're thinking, wait a minute, that's not a compound, which is correct. But when chlorine shares an electron with itself, it makes Cl2. Oxygen does the same thing with O2. Nitrogen does the same thing with N2. And so those are still considered molecules. So a molecule doesn't necessarily mean that it's a compound. Molecules, when we use that word, is saying that it is a compound held together with covalent bonds where electrons are being shared within it. So all of these instances, the electrons are being shared between the two chlorines, the nitrogen and the hydrogen, and between the water in the hydrogen and oxygen within the water. So there's subcategories of covalent bonds. This is just a brief flyby. We're going to dive into these topics more as we proceed through the unit. So the one thing that's unique about covalent bonds is sharing. Now, this is kind of like toddlers. Some toddlers share really well when they go to preschool, and others are like, nope, I am not sharing my toys with you. And basically, molecules work the same way. So, nonpolar covalent bonds are where things get along and they're great. And so, this is usually when you're sharing something where it's elements of the same type. So, for example, chlorine. If it's like tug of war and it's pulling on those electrons, deciding who's going to get more time with those electrons over the other atom, it's kind of going to be a draw. So if you played tug of war with yourself, you would come to a tie or a draw. And so that blue represents the electron cloud. The black little dots there are the nucleus. And so the blue is showing that it's symmetrical. And so the idea there is that if we cut it in half, that the electrons are equally dispersed. We can see a difference in this next image with the electron cloud is that still that blue, but it's lopsided. And that's what's called a polar covalent bond, where electrons are not shared equally. And this is when you have one element that's more electronegative than another. And so another term that's a blast from the past. We've talked about electronegativity and its trend with the periodic table. We're going to be using electronegativity within this unit. And so electrons are not shared equally. And so we get these partial opposite charges. So there's another Greek letter here. And so it kind of looks like an S or a D that just kind of tails and curves all the way around. And that just represents partial. And so the electrons are spending more time here. So electrons are negative charge. So this means this region of the compound, or the molecule, I should say, takes on a negative charge. The electrons spend less time here, they take on a partial charge. And that's going to become very crucial to when we get to begin talking about intramolecular forces. And so that's later on in this unit. So how can we compare properties of these two bonds? Because different way of the electrons being shared result in different properties. Again, just a comparison in terms of what's happening. Ionic is the transfer of electrons, covalent is the sharing. So melting, we can see a very key difference between these. If you put table salt in a pan on a stove, you can spend all day and you are not going to melt that. It's very, very high temperatures that are required. However, you go to light a candle, the wax begins melting right away. That is low melting point, and that's what wax has, or paraffin. Soluble in water, so soluble means can it dissolve or not? Well, if you take that salt and put it into water, you can make a saltwater solution. So yes, it does dissolve. You put wax into the water, it is not. However, it says usually. For example, sugar is held together with covalent bonds. You can go and make Kool-Aid, and that does dissolve. So there's some reasons with that polar, non-polar on when something will and won't with covalent. But overall, we're going to say no. So the next thing is we can conduct with electricity, or test for conductivity. We have conductivity meters. Some of them make a light to indicate that an electric current is being carried, or they'll make a sound, or some do both. So does it conduct electricity? In ionic compounds, it's a yes. So it's because there's that transfer of electrons. They're moving through. Oh, there goes Shaylee. It's like clockwork. She knows I'm about done, and she's being a tiny little toddler with a temper tantrum. So I think she's good now. Okay. So the last thing then is covalent does not conduct electricity because there aren't electrons moving around like an ionic compound. And so some other properties, ionic compounds, again, that key characteristic on how they bond together, they tend to have a crystalline three-dimensional shape that we can then see at the big level. And then covalent, they tend to make molecules, and a lot of times these are liquids or gases at room temperatures that tend to have a strong odor associated with them. Gasoline, for example, has lots of covalent compounds in there. If you used nail polish remover, formaldehyde is a preservative for specimens. If you've ever dissected something, they usually don't use formaldehyde. They use other preservatives that you can tell don't have a good odor, and those are covalent. Ammonia, household cleaner, that's covalent as well. So they tend to stink. Again, the type of elements we find in it, ionic is metal, nonmetal. Covalent is only nonmetals. You will never have a covalent compound with two metals. So sometimes compounds have a mixture of both, and that's when we have a polyatomic ion. If you remember polyatomics, here's some good examples down here. So this polyatomic part here, the phosphate, is phosphorus and oxygen, so two nonmetals. So that individual part is held together with a covalent compound. However, if you remember, phosphate is a negative anion with a -3 charge. Sodium is a +1 cation. That part is then held together with an ionic compound. So the polyatomic within itself is covalent. The overall compound is then held together with an ionic bond. Same thing here, the sulfite is held together with the covalent sharing of electrons with the sulfur and oxygen, which then bonds with the aluminum that part of it is a um, ionic bond. So again, this is a mixture of both covalent and ionic. So the last thing we're going to do is determine if this is ionic or covalent. Some of its using properties. The first five are based on the chemical formula. So this first one, we have a metal, non-metal, sodium and chlorine. That means it's an ionic bond. CO2 contains a non-metal carbon, non-metal oxygen, two non-metals make it covalent. Water. If you remember, yes, it's a positive charge here. It is a non-metal though, okay? So hydrogen's kind of an odd duck when it comes to classifying. So this is covalent because again, it's two non-metals. So then we have iron and oxygen. Iron is a metal, oxygen is a non-metal, therefore it is going to be an ionic bond. This one is a weird one. We have gallium acetate. So we have the acetate part, which is going to be covalent, gallium, which is a metal, so that's going to be ionic. So it's both. Based on the property chart above, high melting point is an ionic bond. If it's a liquid or gas at room temperature, that is most likely going to be covalent. Ionic compounds are solids at room temperature. And then if it will not dissolve, that means it's not soluble in water. That is covalent as well. So I'm sorry you got to listen to what life is like here at my house with the rabbit sometimes not cooperating. If you have any questions, need help on the homework, just let me know, and stay warm and stay safe.